In this module, we're going to work out an important example of general measurements. We're going to see how to perform a partial measurement on a bipartite quantum state. So let's do an example. Let's take a bipartite state psi, which is initialized in the EPR pair. This is a state that we've worked a lot with already, and I can write it as 1 over root 2, 0, 0 plus 1, 1. And now suppose I want to perform a partial measurement on this state. I want to measure the second qubit in the standard basis, and I want to describe completely what happens to the system. So once we've decided what we wanted to do, the first thing is to figure out what is the POVM that describes the measuring operation that we're trying to perform. And here we're measuring the second qubit in the standard basis, and we're not doing anything to the first qubit. So it's natural to introduce the following two measurement operators. M0, this will be an operator that does nothing on the first qubit, the identity. Tensor, the projection on the standard basis state 0 for the second qubit. And similarly, I can define an operator M1, which is the identity tensored with projection on 1 on the second qubit. Now I claim that these two matrices together form a valid POVM. Let's verify this. I need to check that M0 and M1 are positive semi-definite, and this is the case because each of them is the tensor product of two positive semi-definite matrices, so that's positive semi-definite. And the second thing to check is that they add up to identity, so let's verify this. M0 plus M1 is equal to, well, identity tensored 0, 0 plus 1, 1. And that is simply equal to identity tensor identity, which indeed equals identity. So M0 and M1 together form a valid POVM. Once we have a POVM, we have everything we need in order to describe the probabilities. We don't have everything we need in order to describe the post-measurement states. I also need to give you a Krauss operator decomposition of my POVM. Now it turns out that when the POVM is given by projectors, the matrices M0, M1, etc. are projector matrices, meaning that they're Hermitian and they square to identity, then it's always the case that you can, if you want, choose as Krauss operators the same operators as the M themselves. The reason is that if I define E0 to be equal to M0, then I can check that E0 squared is M0 squared, and because M0 is a projector, this is equal to M0, and so the rule for the cross operator is satisfied. Same thing, I can set E1 to be equal to M1, and then I will have that E1 squared is equal to M1 squared, which is equal to M1. So I have a POVM, which is given by M0 and M1, and I have Krauss operators, which again are given by M0 and M1. So E0 is simply equal to M0, and E1 is simply equal to M1. Now, given that I have my POVM and my Krauss operators, this is enough data to specify how the state is going to evolve. So let's see this. So we have our state, the EPR pair, and we have the POVM that we want to perform on this EPR pair. Now let's see what the probabilities of the outcomes are. So the Born rule says that the probability that I obtain the outcome 0 is given by the trace of the product between M0 and the density matrix associated with my state. Here I have a pure state, so the density matrix is simply the rank 1 projection on the pure state. Now this is equal to the overlap between the state psi and my measurement operator M0. And this you can compute. So if I look at the overlap here, let's compute it explicitly. So I'll get 4 terms. These terms will look like 0, 0. Then I have identity tensored 0, 0 and 0, 0. Then I have 4 such terms. So now you see that a lot of these terms are going to be 0. The second term is 0 because you have the 0 and the 1 here. You can cross out. So this is 0. This term similarly is 0, and the last term similarly is 0. The first term, however, evaluates to 1. So what you get for this overlap is a half. as you would expect, right? We're measuring the second qubit of the EPR pair in the standard basis. We know intuitively that the outcomes should be a half, probability a half we get 0, probability a half we get 1. And so indeed this is what the case is here. We've done the calculation for the outcome 0, and the same calculation would reveal that the probability that you obtain the outcome 1 when you perform this P of M is again equal to a half. So this we kind of knew. What we didn't know, however, is what are the post-measurement states. So that's the interesting part, and let's evaluate those using the rule that we saw. And that rule says that the post-measurement state associated, let's say, with the outcome 0, this should be simply renormalized E0 psi psi E0 dagger, renormalized by the probability of the outcome 0, which here is a half, so I should divide this by a half. Now E0 is equal to M0, which is this identity tensor project the second qubit on 0. And so when you apply this to psi, what you get is that the component of psi, that is when the second qubit is equal to 1, this gets projected out. The product becomes 0. And so when you do this calculation, what you get is that the only term that's left is the part of psi that corresponds to this second qubit being 0, which is 0, 0, 0, 0. So that's quite interesting. You see that we've measured the second qubit of the EPR pair in the standard basis, and we're asking what the state gets projected to, the state that's consistent with the second qubit being equal to 0, which is the 0, 0 state. In particular, the state of the first qubit is also equal to 0. Similarly, we could do the calculation for the outcome 1 and see that in that case we get naturally the 1, 1 part of the state. So in your homework, you'll see that this property is in fact valid whatever basis I decide to measure the second qubit in. That is, if I choose any basis of C2 and I measure the second qubit of an EPR pair in that basis, then the whole state is going to be projected down to a state that's the tensor product where the second qubit is projected in the basis vector that I obtained, and also the first qubit is projected in the same basis vector that I obtained when I measured the second qubit. And that's a property that arises because the EPR pair is an entangled state. If it was a separable state, then this wouldn't be the case.